Hey there, and welcome. Today, we're going to dive into the story of one of the most fundamental ideas humans have ever had. Numbers. Seriously, it's a tale that starts super simple, just counting stuff, but it ends up describing the very fabric of reality itself. So, let's get into it.
I mean, it seems like such a simple question, doesn't it? We use them every single day without even thinking about it. But have you ever actually stopped and wondered, what are they? Where did they come from? How did we go from just counting on our fingers to this incredibly complex system we have today?
And believe it or not, this is where it all begins. The entire infinite universe of numbers we can possibly imagine, it's all built from just these 10 little symbols. That's kind of mind-blowing when you stop and think about it, right? Just 10 pieces to build, well, everything. So to really wrap our heads around this whole universe, we have to start with the smallest possible parts, what you could call the very atoms of math. And here they are. These are atoms, the digits. It's kind of like how a limited number of chemical elements can combine to make a bazillion different molecules. These 10 digits are the basic building blocks for every single number you have ever seen or ever will see. And this is where the real magic starts. We have a totally finite set of tools, only 10 digits, but with them, we can build an endless, infinite number of, well, numbers. There's no such thing as the biggest number, because you can always just add one more. This amazing contrast is really the engine that drives the entire system. So how did we get from just those 10 digits to the huge number line we all know today? Well, it didn't happen overnight. It was more like solving a series of puzzles where each new set of numbers was invented to fix a problem that the old set couldn't handle. Okay, first up, we've got the natural numbers. These are the ones that just make sense, right? They were born from the most basic human need to answer the question, how many? How many sheep do I have? How many people live in this village? You start with 1, then 2, then 3, and you just keep on going. But that simple question points out a pretty big hole in the system. Natural numbers are fantastic for counting things that are actually there, but they have no way of representing the idea of, well, nothing, the complete absence of a thing. And boom, the solution was a total game changer, the number 0. Just by adding 0 to our family of natural numbers, we create the whole numbers. And this wasn't just some new digit. It was a massively profound idea that opened the door to way more complex math. All right, so we've got 0. Problem solved, right? Well, not quite. Another puzzle popped up. How do we represent ideas of opposition? Like if having $5 is 5, what is owing $5? If it's 10 degrees outside, what's 10 degrees below 0? So what do? We expand the family again, creating what we call the integers. This set takes all the whole numbers and gives every positive number a negative twin. All of a sudden, our number line wasn't just a one-way street. It became a true line, stretching off to infinity in both directions, positive and negative. Okay, so we've got our basic number line stretching out in both directions. Now let's switch gears a bit and look at numbers in a different way. Not just where they live on the line, but by their actual inherent properties. What's their personality like? The first and most basic way to slice them up is even versus odd. And the test is super simple. Can you divide it by 2 and get a clean number with no remainder? If you can, it's even. If you can't, it's odd. Every single integer on that line falls into one of these two camps. And then things get even more interesting. We can split them up again into prime and composite numbers. Primes are like the ultimate building blocks of numbers. They can only be divided by 1 in themselves. Think of numbers like 2, 3, 5, or 13. Every other whole number bigger than 1 is composite, which just means it's made by multiplying prime numbers together. For example, the smallest composite number, 4, is just 2 times 2. This is a huge deal in math and is actually the backbone of modern data encryption. All right, so we've mapped out all the solid points on our line, the integers, and we've sorted them out. But now we're about to take a huge leap into the vast empty spaces that exist between those numbers. Just think about that number line for a second. We've got our dots for 0, 1, 2, and all the negatives. But what about all that empty space between the dots? What about 1.5, or a third, or 0.25? Our system of integers has no way to even talk about those points. This is where the massive family of rational numbers comes in to save the day. And the rule is actually pretty simple. If you can write a number as a fraction, one integer over another, it's rational.
This is a huge group. It includes all the integers we've already talked about, because you can write any of them as a fraction over 1. But it also fills in all those gaps with things like a half or 3/4. But just when they thought they'd filled in all the gaps, mathematicians stumble onto something weird. Numbers that just couldn't be written as a nice, neat fraction. These are the irrational numbers. Their decimals are just pure chaos. They go on forever and ever with no repeating pattern at all. The really famous ones are numbers like pi or the square root of 2.
And this right here is the perfect way to get it. We've all probably used the fraction 22 divided by 7 to do some math with pi, right? Well, 22 over 7 is a rational number. It's a close guess, an approximation. But the true value of pi, that's irrational. Its digits go on forever randomly, and it can never, ever be perfectly captured by a simple fraction.
So, we've got all our puzzle pieces on the table. The integers, the rationals, and those wild irrationals. Now it's time to snap them all together and see the big picture. And here it is, the grand finale. The set of real numbers is simply what you get when you take all the rational numbers and all the irrational numbers and throw them together in one big pot. They account for every single possible point on the number line. No gaps. So let's just do a quick recap of how we built this thing from the ground up. We started with the simple natural numbers for counting. Then we added 0 to get the whole numbers. We threw in the negatives to build the integers. Then we filled in all the gaps with fractions to get the rational numbers. And finally, we added in those strange, patternless, irrational numbers to get the whole shebang, the real numbers. Each step just wraps around the one before it, kind of like a perfect set of nesting dolls. And the end result? It's this beautiful, perfect, unbroken line. Every single point, every possible distance from 0, whether it's positive or negative, a simple fraction or an infinitely long decimal, it finally has a name. This is the real number line. So, it feels totally complete, right? An unbroken line that seems to cover every possibility. But what happens if you ask a question like, what's the square root of a negative number? The real number system just breaks. It can't give you an answer. And that very question opens a door to an entirely new dimension of numbers, a place where numbers can actually be imaginary. But that is a story for another time.